Good. Cool. So, yeah, so you can see anything. Okay. Now, welcome back from fall break. I like it. I like having like a cheerleader here. Yeah. Let's hear it for Joy Laugh. Let's do a wave. Yeah. Okay. So, first you all are refreshed and ready for action from break. I posted in your homework yesterday. But because you're so refreshed and happy from fall break, you will take this as its title, Joy Lab. You will view it as such. It's 4 wonderful little exercises. And I spent a lot of effort trying to make them less formidable than they were when they were called Pod Lab. But they're diverse, and they're exciting, and they used to be the hardest exercise in the class, and I've hopefully managed to make them less so. So, with further ado, I'm just going to show you what's up here. Let's just walk through that. Piazza. Let's get to the right class. Security. But please feel free to ask questions in the class. Out of all the installations I've had for this course, this is the one that has the fewest, least volume of questions from students. I suspect this may correlate with the number of students who are like, I have no idea what's happening. I'm enrolled in this class, but that's about it. or if you feel stuck or there's something that's unclear, please come see me. I'm happy to see you guys. Anyway, so let's see what Joy Lab is all about here. Okay, can I just unpin this? Aha. So, 4 things. Our next bit has been configured for 3 of these. So that means that we can't just return to a shelf that's over in the stack or on the heap. So, Durka, aptly named, is the first of the bunch. And so if the thing Lipsy or Rock means something to you, that might be a good strategy. Recall that there's an exploit in /labs that it's a Python exploit that could be useful for constructing some of the more involved format string vulnerability. So that's something we're going to go through and walk through today. We just did it kind of at 200% speed before fall break because everything was so intense before break. So now we're all relaxed and so we did our yoga routines and stuff, and now we're just going to go through the format string. And then I have here this mysterious heap overflow vulnerability, which it's a binary that has been linked to 4 different memory allocation implementations. So you will have the source code for all of these. You'll know exactly how malloc is implemented in the red version, the green version, blue version, purple version. I have successfully exploited one of these. I haven't checked the others. I just picked one and did it work. And I'm not going to tell you which one it is, but I think you can kind of figure it out. Right? That being said, it's kind of cool to see 4 implementations of how you could do malloc. There's red-black trees, and skip lists, it's all you know. You only need to solve one of these to get the privileges of the F3 user, and then you're done with that part of the exercise. And then there's Spectre, which is just this is enabled, show me what you can do. So, if you solve 3 of these, you have full grade. If you solve 4 of these, you have 110% of your grade for the exam. And the way the grading works is that you solve 1, you get 40%, solve 2, you get 70%, 3, 100%, 4, 110%. Okay? So, should be a fun challenge. Right? It's due on the 25th at 11:59. And I don't think we can afford many more extensions for this semester. That's one of the things that's going to happen probably next week is that I'm going to be giving out the presentation topics for each of you, possibly in pairs. I haven't decided yet. I'm going to pick some topic and make a YouTube video about this topic for 15 minutes, where you become the expert on the topic, and you're going to be speaking from authority about very beautiful, clearly written slides about what it is that makes that particular topic exciting and compelling and cool. And I'll have a list of topics that you can choose from, but you can also add your own. So that's a little bit about homework. Any questions? I'm going to walk like this until
So
Yes.
in the last homework, you said something about the cat, SC cat thing. Can you show us how you,
What
that
did
meant?
you say, SC cat?
So you know how you were piping in the input, you said to like cat it in.
Oh,
Can you
yeah.
explain what that meant?
Yeah, so something that happened during the last expo, some people were like, oh yeah, there's, let's say it's overflow, I don't know which one it was, like overflow 3 or something. And you could be here and you could say like, hey, this is my first argument, right? So that's how you like, how you input that. And then you're like, well, actually, I also need to read in from standard input. And the way people did that was using this instruction. What is this instruction? It says, pipe into the standard input of this program the contents of a file. Now you specify the file name. So for instance, if I say here readme, then anything that's going to be read from standard input is going to be coming from readme. Now, what some people landed in trouble with was that if you successfully spawn a shell, the shell is going to spawn and be like, yeah, tell me something to do. And it's going to be reading from standard input. Except, by the time you input your shellcode, standard in gets closed. And so the shell is like, oh, there's no standard input. Okay, well, I guess I'll just show myself to the door, right? It just turns off. And so what you will notice when you run your exploit is that nothing happens. And you're like, right? The Hulk comes out, right? And the way to fix that is that instead of closing the standard input file descriptor, now completely equivalent way of doing what I just wrote here, is to say cat readme and then pipe it into overflow 3. Completely equivalent, but again, when you're done taking every line of readme and feeding it to standard input closes. So what we're going to do instead, and this is the trick that you were asking about, is we're going to have several commands here. We're going to have cat, and then just add another cat over here. I mean, there can't be too many cats, right? It's the day of the internet. Ha ha ha. Okay. So here, what happens is that you open up the file and you take everything from it, and then you just expect the person who's running this exploit to start typing information, and that's going to get input as standard input into the program. Does that make sense? On the scale of 1 to 10, how much sense does it make?
That's nice.
Oh, it's actually very useful information, right? Yeah, it's a distribution. Yes, okay. But I think the median was something like 6 or 7, right? Right? Yeah. Good, okay. That's about half. Okay, so here if I start typing stuff, and right now the program has stopped executing, so the whole thing is just going to die, right? Because it's too close. But anyway, this is the way you would do it if you need to pipe in information to standard input. That's very useful to know. Any other questions about?
Alright, so the first cat is reading in that file,
Yeah.
and the second cat is just kind of like left, so that you
Yeah, I mean, you can do whatever. You can just chain commands here together. You can catalog the file. I mean, completely equivalent, you could do this. What this means is that cat first the file called readme, and then the file called, special character, it says standard input. Right? It just minus is the standard input thing here. So if I say cat minus, hello, help, right? Just reads in the line that I typed, and then echoes it back. Right? Okay. Make sense? Yes?
In general, what is actually happening when you put several commands in parentheses?
Yeah, so it just means that this block here of like cat read me again, whatever it is that you want, cat, these things are going to be executed in sequence. So one and then the other and then the other and so forth. And the collective output of all these things is what you can then, for instance, pipe into something else or do whatever it is that you want to do with it. It just says all these things are bundled together. It's just nesting like that. Now, in Bash, you also have things like, you, for instance, say like, hey, I want to cat read me, and if it is successful, I want to continue to the next command. So if this is true or like works, then I want to do that one. But I always want to do this one here after that. So you have kind of these types of expressions. Bash is actually a pretty flexible scripting language. Make sense? You do really cool stuff. Same thing here. So it's catted the thing twice, and everything was great. Cool. Anyway, let's write a format string actually. Do you guys remember? Okay, do you remember what format strings were?
It would be like F brand makes the center sign.
Ah, yes, okay. That's one out of how many?
Well, it's 39 were involved, right? So.
Yeah, about that. There's not 39 people in here. So, let's see. Anybody else remember what form of strings? How many people remember what form of strings were? Just the form of strings. Okay. Well, let's just write a little program then. So just to remind ourselves how it works, right? This is in class. Let's see. So I'm just going to write a little C program here, and it's going to be a part of string here. Somebody commented that I type fast. I am an embarrassment to my group of friends how slowly I type. Like I'm like half speed to them. I'm like, it's all like clunky. Anyway, just for whatever reference you have. So printf, let's do hello there, and let's put a number. And we can put 42. And now if I compile this, it prints hello there 42. How did that happen? Well, it happened because I had a format string, which is an initial thing within the quotes. So it's a fixed string that specifies inside of it special characters that are interpreted by the printf routine to bring in extra information. In this case, it says like, hey, take the next argument that you provide and treat it as a decimal integer, the assigned decimal integer. In fact, if I didn't want it to be signed, for instance, if I put in minus 42 here, what do you think is going to happen? What will it print? I said it was signed decimal integer. So what will it print right now?
A really high number. So interpret it.
Any other guesses than that? I said it was a signed number. Minus 42, yeah. Double tricks. Yes. I make the worst multiple choice questions. Like people like that. Yeah. Anyway, sorry, I'm just being snarky. Here's, if I put U here, that's unsigned. So what's going to happen now is something like you said. Right? So U just means unsigned. And we can combine these little identifiers together and make, for instance, like I want it to be long unsigned. So let's see if this changes anything. Probably it's going to be the same thing. Yeah, it's the same thing. And I can make it long, all sorts of little things like that. Kind of very useful, right? Now, it's not just printf. I could even have here something called scanf, where it's just like, I want to scan from the standard input, and I want it to be a digit, and another digit, and then a string, okay? And I'm going to put the first one into number 1, number 2, and then I'm going to have like a buffer here, current buff 128. So I can say n1, address of n2, and then I say actual buffer. Okay? And let's just say that I print out here the numbers that I read. Then B, and then put an S here. And so put a new line here for fun. And that's going to be n1, n2, buff. This makes sense what I'm doing so far. I'm just going to read something in and print it back out. This is the standard C way of doing it. And just to quench that warning, we return 0. This returning of 0, by the way, when I said that I could have the cat readme and then ampersand cat readme, how do you know whether or not cat readme was true or false, right? Well, it's determined by whether or not it has non-zero return code. So if a command executes properly in the Unix environment, its return code is 0. If it's -1 or any other number, it's viewed as an error. And so like if you chain things together with this kind of and operators, that's what it's looking at. It's the return code from main. Okay? So let's make 32-bit just for fun. Uh-oh. Expects type car start, but argument for its type car start, 128. Oh, that's such a pity. What about now? Okay. Cool. So what's happening right now? Why is it waiting for me? Well, I haven't provided anything just on input, right? It's just scan up, it's here. So I could type here like 42, 9,000, hello. Okay. Nothing mysterious so far, right? What happens if I type in here 42, 9,000, then and like a really long Actually, how do I provide it with a really long right now? Oh, how do I Perl stuff? Tell me what to write. So do I type it where? I'm going to specify it to standard input. So what's the trick? All these things, so I can cat things. I can even say here, like, Perlman C, print, and let's just print 42, 9,000. And then let's just add to that string A times, any suggestions? 1,000? Okay, and now I'm going to pipe that into class. What's going to happen? Oops. Oh, circle. Why is there a circle? Say again? Yeah, so scanf didn't care. In fact, it overrode my instruction mode and everything, right? It's an example of an overflow, just like all the others, right? But there was nothing that was specific to us using a format string here. It was just that we noticed that, like, %s, you read in a lot, right? And because of things like that, scanf, it can tell you, like, hey, I actually don't want just a full string here at any length. I want at most 128 characters. Let's just see if we can specify this. Maybe even 120. So supposedly you can do this. Let's see if it actually works. Make class. So I'm just gonna GCC again. And run it again. Oh. What's this?
Because it only reads 128 characters, and at the end there wasn't a null type, and whatever's left there just gets printed out.
Yeah, it just keeps printing up to 120 characters, not including null type. Scanf doesn't include null type. So you can have really funky stuff happening from that. You can actually have null type from that. So whatever's previous in the buffer, here it is. What? However you pronounce that. Looks like French? No. Anyway, so we can put some limits on things, right? So it's pretty flexible, the kinds of commands you put it on format string. Now, the issue that I mentioned in last class, though, was a little bit different than this, right? Here on this screen right now, we have 3 fully specified format strings. They're constants. They're strings that are embedded in the program. They're within the double quotes, right? So we're not impacting them in any way, right? But what if we could? What if, for instance, I changed this around a little bit and now I typed printf hello, no, not hello, printf buff. Now what printf is expecting is that the first argument is a format string. It doesn't differentiate between there being a constant string and there being something that you generated yourself. It's just the character array. Which means that now we have a different attack vector, right? So here's my program again. Everything is the same. Let's print this to see here. What should I type now to crash this program? Now, because of the printf buff, buff is to be interpreted as a, instead of like, I'm just going to have 10 or something. In fact, I'm not even going to have a format string at all. I'm just going to printf stuff. I'm going to 42, 9,000, then hello. It always has to be said with an English accent. Okay? So these are printed. Something funky is going on. So buffer isn't clear, so we get all this like kind of leftover stuff. Let's just for clarity, I'm gonna do a memset here. Memset buff. Buff 0, size of buff. Size of buff. So no, you see? And let's run this again. And now it's much more clear because now even though scanf doesn't null terminate, there's a bunch of nulls in the function. How do I press this program? Talk to me. We know we can't put in a bunch of that was forwarded by us putting a limit in the scanf, right? But there's a second bug. Well, what we discovered last time was that we are the format string now. So what gets printed here? Printf invalid. Oh yeah, I shouldn't be using printf for this because that's going to be interpreted very differently. Let's echo this. Aha. Ooh, why is this happening? This is happening because inside class here, the last string that I read in is being printed and interpreted as a format string. Therefore, every time there's a % in there, the next thing is going to be this special identifier or command, if you like, to printf to do stuff. And printf has no idea that there aren't more arguments for it. It doesn't know that there's just buff and that there are no more variables like the M1 and M2 and so forth. It has no idea. It's just going to look at 8 EBP, 12 EBP, 16 EBP. It's C. It's just, you can do whatever you want in C. There's no limit on it. In Java, you probably get like out of index exception or something like that. Not so for C. And remember that all your devices are running C code. Yes, that's right. So, this is where we were. But we went a little bit further than that, right? We found a way to not just be able to read stuff. So let's actually play a little bit around and read stuff. So a little bit further. Let's just keep reading things. What do we notice? So keep reading things. Some of these look like kind of familiar addresses. This is like a stack address or something. What? If we are printf for 20, yeah, this is the hex to my first piece. Why is it being printed, right? If we think about us being printf right now, what we're doing is that we're saying like, oh, %p. Okay, I'm going to look at 8 EPP. Oh, I see another %p. I'm going to look at 12 EPP. We're going to keep going up EPP. And what is 8 EPP? It's something that's belonging to the stack frame that called us. What stack frame is that in this case? If you look at this class, what stack frame is calling printf? Main, right? And what's on the stack for main? If you're all trying to look away, it's okay. I still see you. Yes. I have eyes everywhere. Little birds. Okay. What's on the side? Prof, right? What's inside Prof? Our stuff, including the string %p, which is what we're printing now, right? So printf is accessing stuff and it's printing out its own argument. It's like turtles all the way down, right? Some self-referential thing. So if I were to type something different in here, if I were to include some other things, not just hello, but like A, B, 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 C, 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 look what prints. That's kind of fun, right? Now, what was the next step that we did last time? We discovered that, like, okay, great, so we can pop the stack, whoop-de-whoop, right? So, what if we needed to pop it really far, right? Well, we had some help. Because if we looked at, say, the man page for printf, man printf, what we noticed is that there's this thing called $. What is this thing here? The arguments correspond to blah, 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 blah. One can specifically which argument is taken at each place when an argument is required by writing $m instead of %. If you actually, like, do the mundane thing and struggle through some of these really boring manual pages for things like printf, you'll find all these little gems hidden away, right? This particular one says, hey, instead of you saying like with a number, I can actually say, hey, take something as an argument for something else, right? So in this particular case, I can say, instead of you looking at just the first argument, look at the 10th argument. Now, why am I writing $? For what? If I just had echo and then just had my dollar in here, what would bash try to do? Yeah, well, it would try to look at it as a variable. It's like, oh, this guy who's trying to execute this echo and then typing a class, he's looking for the variable $p. Let's see if it's there. Oh, it's not there. I'm just going to put the empty string. Very frustrating. We'll just put the backslash when you need it, right? So I'm going to put it in here. And now, do you notice any difference between what we printed? Instead of the 2a, I'll now have something completely different. Right? So I'm able to control where it reads, which is cool. This is a very cool information disclosure vulnerability so far. We're going to take it even further than that, right? Do you remember what the trick was to actually get something right place? What are we going to do? There was a special percent. Yeah.
Was it percent N? What was it? But essentially, it writes the number of bytes and something.
Yeah, there's something like that. Right, so let's see why this exists, and just give an example here. Look at the class over here. So if we do like scan, if we print, what I could do here instead of just percent, I could type in percent %n and say, hey, actually into like n1 right now, n1 contained, I could just tell printf to print how many characters it's output to the terminal into a variable called specified by an argument. Here's the n1 address. Let's see how this normally works. I'm just going to create a class. n1 contains 22. Why does it contain 22? Let me do it slightly different here. I'm going to put percent %n here and another one here. I'm going to put that as this one as n1 and then second one as n2. Okay? And then I'm going to print them both out. All right, so I have a percent %n at the very beginning of the line, and after this hello there stuff, and I'm going to have you guess what's going to get printed now. I'm going to make this. Okay, I'm going to run this, but before I run it, I want to know what the output is. What's n1 going to contain? I had a percent %n at the beginning of the line.
0.
0. The number of bytes that have been output are 0. Nothing has been printed yet. And then 2 is going to contain 22, like it was before, right? Ta-da! Does this make sense? It's like the most useless feature you can imagine. Like, why would you need this, right? It's like, yeah, if you want to measure how many bytes you wrote, and you want to do it in a shorthand, and you want to do alignment or tabs or something crazy like that, right? Then, yeah, this might be helpful. But it's so helpful to us hackers, right? Make sense? Okay, all work. Good, so we have this thing that can write to places. So what would happen now if I changed my vantage point here, instead of typing here 10p, or let's find like, let's say 12p. Ooh, that's somewhere inside our string. Let's instead do 12p, let's do like 14p, or even, let's go in the other direction, 4, 5. Okay, we're finding some addresses right here. Ooh, we're finding something very interesting. Look at how that changed to now 41441. If I change my p now to n, what will happen? Did we have one n? What will happen? printf is going to interpret this. And it's going to be like, oh yeah, take the 6th argument, which is on somebody else's stack frame, which we know now because we had it as P before, we know it's 0x414141. I'm going to look at that as a pointer to an int variable. And I'm going to write to that pointer the number of bytes I've printed out so far. That's a mouthful. And so I would expect it to try to write, what exactly? 4, 8, well, this is 5, okay, this is 12, 13, 14, 15, 16, 17, 18 into OX. Just address it here. That's what I would expect to happen. If I had like had it here, like a P, this is what I printed. This is what the address looks like. I view it as a pointer. Now if I view it as a pointer that I'm going to follow and write stuff to, this is where I'll try to write to. And the number I'm going to try to write is how many bytes I've printed out so far, which is something like, what was it, 18 or something. So let's see what happens. Sec fault. Let's look at the sec fault. Okay, GDB, class, core 9755. Uh-oh, what was it trying to do? So I'm running, what's the program counter right now? It's trying to write the value of ECX into the pointer from EX. Somewhere inside printf, this is what's happening. So we want to know now, what is inside registers EAX and ECX? Oh. So this is the decimal version of the hex here. So the number 18. So this name. We wrote a number into an arbitrary memory address. This should get us extremely excited, especially since this is a 4-credit course. Very cool. So how do we abuse this? 3-credit course. I'm sorry, yeah. Just twitching me over there. Yeah. Fine. Okay, only 3 credits. So just get 75% excited. Fine. What do we do with this? What do we do with this information? As hackers, what do we want to do with a target? Normally, right? If we're able to inflict any type of damage to it, in the sense of like changing things in its memory, we're doing pretty corrosive stuff in the program. The program is probably going to crash after we've done it. But before it does, we want to kind of, we want to be like the parasitic wasp, right? We want to get something done before that happens, right? Anybody know the parasitic wasp? I find a really cozy little YouTube video to watch. Okay. Yeah. What do we want to do? We'd like to have it do something on our behalf. Ideally, hand us a shell. Be nice, right? Because after the shell executes, it's tabula rasa. It's like everything's anew. It's just, oh, you've been transformed into this shell that's obedient to the commands of your master, the hacker from afar, this little 13-year-old in a different country. And everything is forgiven, like nothing is crashing. That's what we want to do, right? But currently what we've been able to do is to write to any address we specify, but just the number 18. We're not there yet, clearly. How do we get there? Let's do some archaeology. In the time before fall break, all the answers were provided. What do we do? We have, somewhere in memory, a place we want to overwrite, right? What place of memory do we want to overwrite? This is to overwrite. Yeah, some return address, right? Why some return address? Well, because then we write to it and overwrite it, and we return from main or whatever it is that we're doing. Good things happen, right? Good things happen to us. The control flow of the program gets redirected to whatever it is that we want, right? So somewhere there is an instruction pointer saved in memory, right? Probably looks something like this. This is a saved return address of 0804 A, B, C or something. So this is like a saved. And this is located at some address. These 4 bytes, right? So what would be what would that look like, given what we've seen? It's somewhere on the, where do we store our return addresses? Yeah, so what's a typical stack address? Something like that, and like whatever we want. It could be, it's Halloween soon. Yeah. Okay, so we need to find this address, we need to write to it. And currently, all we can do is that we can write, what is it, 12? We can write the number 12 to any address. So we could write that over. Yeah. So we could technically overwrite a return address with 12, right?
You can't bring common characters with one before.
Yeah, so somehow like, there's nothing interesting going to be in the address 12, right? You said some characters before it?
You can't bring common characters with one before.
Yeah, we can change that, that's right. So we could add more things and increase this number, right? So instead of being OX12, it could be, if we write 15 more characters, it could be OX21, right? Or something like that. We can change it to whatever we want. Well, not whatever we want. Within the bound of reasonable. We cannot make this be whatever arbitrary address we want it to be right away, because that would involve us trying to print out gigabytes and gigabytes of data through printf, which is going to choke, right? So that's not going to work. So what can we do? Well, first and foremost, let's at least get to the stage where we're overwriting a return address. So now I'm faced with a little dilemma here. I could look at my core file and find a return address, right? I could just look through the stack and find it. So that's what we've been doing so far. I want to show you a little trick, right? So notice how we've been getting addresses here from the stack, right? Through disclosure, through our %ps, right? Is there anything that would preclude us from just getting more addresses, including, say, a return address or something from the stack there, through %p? No? In fact, some of the exploits that use former strings are interactive like that. They're just like, well, actually, %p is probably what the address is. Oh, great, right? This is very helpful when there's, say, randomization. All right? You know exactly what you're saying. Let's do that. So what do I need to enter now to get to the stack point? Or like to get to the right location in the stack so that I'm finding a saved return address? What do I need to do? I need to type %, something, $P probably, right? The question is like, what is this? How far do I need to go, roughly? What?
The size of the buffer?
Yeah, I need to get past the buffer that I'm reading from, right? Which is the buffer that's living inside main. And whatever variables main has, right? So how big was the buffer again? 128. Okay. So what should I type here to just print out the right number? If I say 128 here, what does that mean? It means that I skip 128 arguments. Each argument is 4 bytes. Ah, so it's a little bit too much, right? So what number should I put in here? 32. Let's look at 32. Nil. Uh-oh. Well, we're not exactly there. Let's keep going a little bit. So we can just explore a little bit. 4. Ooh, daunting. Everything is kind of awful. We can keep going like that. Let's just go. Oh, we're starting to see something. That's 37. That's 38. Let's do 39. So there could be like extra stuff because of padding. And now we're looking at 40. Oh, what is that? 40. 41. Ooh, these are some addresses that look very juicy. 42. Oh my lord, this is, oh my god. What's happening here? Oh, I'm seeing something so cool here. Okay. Now why do I keep going here? Yeah, I'm kind of looking for, ooh, what could that be? Oh wait, no, darn. So that can't be a frame pointer. Now, part of the problem here, and this is a problem that may actually end up being a big problem here, we need to re-orchestrate, is that we're in main. Nobody really calls main, right, per se. Does that make sense? Which means that there isn't really a picture to begin with, right? We're trying to go to the upper thing. This is why almost all the exploits that I've given you so far have things that are happening inside some sort of routine called, I don't know, or vulnerable overflow, something like that. And we're going to do exactly that now. We're just going to change the game, because we can. And then we're just going to do return on, or like return on, and then return 0. So let's do that. So GCC again, and let's do this again. So now let's try 32. And then, well, okay, we'll have to go a little bit for 34, and we'll probably have to go all the way up to like 38. Notice when you're searching like that, if you think about it, suppose this is like you're hacking the, I was going to say Pentagon. Of course you're not hacking the Pentagon. You're hacking the server that somebody graciously gave you permission to have, right? They may work at Pentagon. And you were trying to find something like this. You don't know where you are. Do you just increment a number and then keep going like that, like iteratively? What would be a better strategy? We wanted to kind of find roughly where something is. Boundary. Binary search, right? Doubling. And then when you hand it, you cut back and it's going to imitate binary search, right? So that's what hackers do as well, if you want to see some code here. Okay, so we're going here, 40, we're going strong. Oh, what is this? Oh my lord, what's happening here? Ooh, it's looking juicy. Oh, what did we just find? We found something that looks a lot like a stack address, followed immediately by something that looks a lot like a program code address. And that pair usually means that we have found a frame pointer and a return address, right? Set to the stack, cool. Now, the whole point of the exercise was that we would find where the saved return address lived. Right? Yes. A little bit off in terms of timing. So we were trying to do that. So what did that mean? So right now, I actually don't know where this 08048523 actually lives. But I know something else. I know that there is a return address 4 bytes away from this address. Why do I know that? It's a frame pointer, and it points to what does the saved frame pointer point to? Another frame pointer. Makes sense, right? You push EBP. It's another frame pointer. So there must be, at this address, another frame pointer, which means 4 bytes away from that address, there must be a return address, right? Should we try it out? So let's see if we can overwrite that return address. So how do we do that? So I want to, so I'm fine printing this thing out. What I'm going to do now is I'm going to try to add something here. Percent 6p. Remember this? So that means that I'm writing, and this is the address that I'm writing to, but I don't want to write to A. I want to write to some other address here. So what address do I want to be writing to? Instead of 41414. given the information you have on the screen.
I thought that the D6 early.
Oh,
Oh, 10. One.
in hex, if I add 4 to 8, I get
C.
C, right? So I have to reverse it again. OC, D6, OX, FF, OX, FF. Oh. What just happened now? Yeah, actually, what just happened? OC. So printed stuff, and then this happened here. What just happened? Everything's a little bit off, right? So I'm printing things out, and somehow, it's because I think I modified something here. The length of the input somehow got modified. So I'm going to need to realign things a little bit. So why are they off? Well, there's one thing that we could check here, which is to just hex dump this. See what happened. Did we actually write OCD6FFFF? Yes, we did, and there's a space before that, and then there was BBBB. Oh, everything kind of looked fine. Okay. So it means that when we are printing out the 6 argument, the things in the buffer are a little bit misaligned. So how can we fix that? You see the address here doesn't start with FFFF. It starts with 42, right? We're off by a byte. How do we fix that?
Subtract the byte.
We'll just add a byte to the string, right, here. So if I add thing here like A, I got a completely different address here. Now it ends with A. So maybe 3 A's, maybe 4 A's. Now I have 4 A's again. So what's happening? This is weird. Now this is actually the fun part about the homework is that it's going to be a lot of things like this. Weird, mysterious things. It seems that there's some character that's not printing out properly when we're echoing it in here. So we're going to need to get to the bottom of that. 23 is a 6. Let's try a different address here. Let's just see if it's, let's just make it FFFF. Oh, that works. So it could be that it's the OXC that's causing grief here. Let's just make it so it's D6, right? And let's make this A0. Okay. And I'm going to make it 0C, and everything goes nuts. So 0C is some sort of special character that's interpreted as, oh, okay, some sort of new line or something. New line is A, D is character return, and this is something else. I wasn't aware of this. That's a pity. Well, luckily, we have actually a lot of influence here. Remember that we're still printing out these addresses here. So if I wanted to shift the stack around a little bit because I'm getting weird characters, how could I shift the stack around? Environment, yeah. Expert, help me. What happens now? Oh, look. I've changed the address to not include my bad character. Right? I added something to the environment, which means that all the subsequent stack addresses are now off by however much, right? So, okay, that's useful. So that means that instead of writing this nonsense here, I can write a different address. So what address do I want now? Instead of the D6OC, I want D5FC, right? Okay, so let's do that. FC D5. Oh, that's looking mighty more promising. So I'm printing it out, and now I'm printing it out again, and I'm going to just write to it. Ta-da. Okay, so what happened? Let's see how we crashed. What have we done? Look at our instruction pointer. Oh, wait, what? What are we gonna do with this? We jump to like something that's clearly not in memory. It's not success yet, right? It's not where we want to jump, is it? Let's think ahead a little bit here. Ultimately, we're gonna need to have shellcode somewhere. So let's just put the shellcode in there, because when we do, if we put it in the environment, we're gonna shift all addresses. So we don't wanna have to do all of them again. So let's just get that over with, okay? And I probably have shellcode, maybe even here, exploit. Here's some shellcode, okay? Yay. Print this out here. So, and I'm also gonna have some, or I can just do program C print. Let's do CC, and let's have 4,000 of them, followed by the shellcode. And I want this to be at the, come on. There we go. At the end of my export egg equals this. So now this is on my stack. Okay, so let's try our exploit again. Oh, all the addresses have shifted again, right? Now instead of it being FC, it is now CC. Okay, so we're going to accommodate that. We can just say CC, and things crash again, and where do they crash? They crash again at the same address. Perfect. Let's turn this into a real working exploit. So what are we going to do? How do we do that? We need to write a full address somehow into where the instruction point is. We've currently just been able to override it, which is great, but just by some like tiny little number.
Try it 1 byte at a time.
Yes, we're going to write it 1 byte at a time, right? Just write that and then like shift it around. So remember this drawing that I had here? Well, we can write this number in, and this is what is it now, 1C or something? And then we could write, I don't know, 1C again, shifted to one address, right? So that means that we would end up with 1C, 1C. 1C, 1C, it sounds like a song. How did this work? So let me show you something. Instead of the B's here, I'm just gonna write the same exact address. No, sorry, I'm gonna shift it by 1. CD, OX, D5, OX, FF, OX, FF, right? And now I'm gonna do another %7, and what have I just done? I'm now looking at the next argument, so popping up, so it should be this address here, CD, and I'm going to be writing that one as well. What do you expect to happen to the instruction pointer following this? Any suggestions? What do we expect to see here? What did I just do? Slave of hands, right? I had 2 overrides here. One of them is dealing with the 6th argument, and when it goes to the 6th argument, it goes into the buffer and it picks out the first thing that I wrote, which is the FFFFD5CC. And then I did the same exact thing again, because there's nothing precluding us from doing multiple writes. So we pick up the 7th argument, which is the one after, and that's the one that has CD at the end, FFFFD5CD, which is 1 byte off. So it's still part of the return address, but 1 byte offset. So what do we expect the return address to contain right now? Yeah, 1C, 1C. Oh. Look, we wrote 1 byte at a time. We did it twice, right? Just a little bit. Did we ruin anything else in the vicinity? Sure, yes. That's what we do, right? That's how it works, right? So, hold on a second, this is good, right? So we could, in fact, if we went all the way here, we could just, what's happening here? Okay. I could write 4 of these, right? Why not? I could have OXC, what's the next one? OXC, okay, good. It always happens, the song, right? And then the next one is, that's right, CF, very good. Okay, so now we have a bunch of addresses in here. and I just added them. Let's see what happened. Oh, did anything happen? D5C8. Okay, we're still okay in terms of addresses. And let's see where it crashed. Is it still happy? Still happy. It's just now there's a different number. Was there a different number? Wasn't it 1C again? Oh, I added some stuff, and somehow there's a different counter, right? You see the balancing game that's playing here, right? So now I'm going to add some more ends. What do I write here for the ends? I'm going to get the 8th argument, and then also the 9th argument, right? Okay, what do we expect to see now? That's right, 2, 4, 2, 4, 2, 4, right? Make a really bad phone number. Right? Okay, so far we managed to modify the entire return address. Suppose I wanted to change it to be, let's say I wanted to have it like 2, 4, 2, 4, 2, 4, 2, 5, or like have the most significant thing be 2, 5. So 2, 5, 2, 4, 2, 4, 2, 4. How would I do that? Very simply. Before.
You add
So-
right to the bit.
So where is that? Right there? That has to be between, right? So before my 9th write, I'm just going to write an extra character. What's the fun character? A? Dot? Sure, dot. It's just a character. Huh? Why did it change? Well, because now, when I did the last %n write, I had written one more character to the output, the printf output, and then that's the number gets reflected, right? So we have some doubling space here, right? So how do we now turn it into an address that we want? Let's have a look inside our core here. What's the latest core? 17.51.9, and let's just look for our shellcode. So I'm just going to do. Oh, wow, that went by really quickly. Where's my egg? Where's my egg? OXCC anyone? S'il vous plaît? Suspect that my egg is not. Export egg equals all this stuff. Print this. Oh. Stupid Python versus Burr. Okay, so now what do you expect will happen as a consequence of this? Oh, my address is going to be off. Okay, they're not like. So this is actually one of the reasons why I kept the original 42p, because as I make changes, at least it will tell me that something changed. Right? It's just a little identifier for me. So now I need to modify my addresses, and what do I need to modify them to? Yes, C6, and this is what, 2C, that's right. And this is then 2D, C6, and then 2, and then C6, and then 2F, C6, and we should be right where we were. Yeah, okay, good. So, the intent now is, okay, so we're going to now look at the last core file we got, and we're just going to try to find our shellcode, 23604. Let's just look for it. Ooh! Yes. We have located it. Okay. I'm going to select this one. It's an informed choice, but it's pretty arbitrary. Okay, this is where we want to go. Our target has been. Okay, this is what we want to write in here. We somehow want to get the address of, like, say, 28. What's it? D3, FF, FF. This is what we want to write in there. And we want to do it in these stages. Okay? So, what do I do? So far, everything is ready except how many numbers there are between Yes.
So for your address, you have to take something where it's like the first bit is less than the second bit.
Oh, yeah. So if it is the case that the first bit is less than the second bit, which is actually not the case here, this is kind of nice, then there's no harm in, so suppose I wanted to have 1C and then I want to have like 1, 0, right? There's no harm in this, right? What if I just keep writing until I pass the 256 boundary, and then the least significant byte is still, it's restart from 0. There's no problem with that. Ah, cute, huh? So, okay, so we need to calculate stuff here. Okay, so right now I already know that the least, like the first one here, the %6 on here, which is the least significant one, I wanted it to be 28. What is it currently? What is the counter when we write it? 24, right? That would be fine, right? It would still land in our knob slit, right? So I'm just not going to bother with it. But the next one is more alarming. I need to get that up to D3. So how many more bytes do I need to write out to get my counter from 24 to D3? All bytes. And then you're going to be like, oh, right. Of course, I am the same exact way, except I bluff. Right? So I'm going to just use the built-in calculator. The built-in calculator will actually tell me the answer. What is it, D3 minus OX, what is it, 24 currently? U. Okay. This is very mysterious. I'm going to show you, just going to show you, oh wait, that was not so successful. Missing the percent sign. 24 D3, right? The significant ones. Now what did I just do, right? Turns out that Bash has this really neat thing. It's a calculator, right? So if I put in dollar and like the bracket things, I can just calculate stuff. I don't know how advanced it is. Not very advanced. Okay. So, but I can do things like OXF plus OXF, and it'd be like, oh yeah, that's 30. And notice that it's returning the answer in decimal, which is what I want, right? Because of the percent thing, it's expecting you to type in decimal, which is human, right? So if I type in there D3, which is what I wanted, and I then subtract it from it however much we'd written currently, it just returns 175. And I don't even have to calculate it, right? I can just pretend that I know, right? But so far, I'm just putting it percent, then 175, and then U. Now, what is the U? This just means that I'm taking the next number on the stack, I don't care what it is, and I'm telling printf to be like, can you print the next number? And by the way, can you pad it so that it's 175 characters? The print's going to be like, sure. It just puts a bunch of spaces or zeros or something, and it prints out my number. And it's exactly 175 characters, right? And I don't have to worry about it popping up on the stack because I am positioned exactly where my things are. I tell it, the 7th argument, 8th argument, right? This percent U could be whatever, I don't care. It'll be 175 characters. So how do I then do the next one? I want this to go up to F somehow, right? So recall, this is where we are. We're trying to get these, oops, the D3 now. We want that to become, no, so what do I write? I'm at the right spot, so I'm right before the 8th argument thing. Percentage to open up that, and then just like there's a built-in bash thing here. And what is it? OX minus how much have I written so far? D3. Close that, and then U, so that I have an actual argument there. What? Oh, do you want D4? I think I have a lot of leeway actually. Let's see what happens. I got FF, which is nice. And I have D3. We agreed this is the address I want, right? Okay, so we're almost there. 3 out of 4, right? We're only going to come to 3 out of 4 because it's just a 3 credit for it. Okay. Okay, so I need one more. So how would I get the last one ready? Get rid of the dot, right? Because I'm already at OXF, right? So what's gonna happen now? What do you think will happen? How many people think this will work? Naysayers, doubting Thomases. I thought it would work. What happened here? Let's see. Dmask. FFF D32. Oh yes. Let's make this actually executable, like executable stack, right? And then let's go back and ask again. How many people now think this is going to work? Oh, trace trap. This is always a very, very good sign. We're near the end. So where's our little eggplant here? Eggplant, okay. So I change this to Nops, Ox90, and what? What? Yet. Okay, well, hold on. C588. Uh-oh. No, C628. It should be right. What is happening here? Okay, I'm going to skip this last one over here. I'm going to put the dot back and just going to see it crash. And then I'm wondering what happened to the eggplant. Okay, let's look at the eggplant. Class, core, 12, 13. Let's just look at our address that we put in here. What was it? D3, 28. Lots of knobs. Everybody's very happy. Lots of knobs. Wow, many knobs. And at the end of the knobs, EB, 1F, all sorts of goodness. CD80, and then what? Okay, then another CD80, that's fine. Then slash bin slash sh, and then a null. Ooh, that should have worked. Oh, no, that should be fine. EB1F. Huh. Okay, so it's kind of a pity, I'd say. Even though we're doing so well. Right, zigzag. Oh, okay, because I changed this. We remove the period. So what exactly happened here? Oh. If you rewind in your head to the very beginning of the class about a common error that apparently I also make. And the file. I provided all the input through my echo, right? And then I just send an EOF and close whatever happens, right? Instead of doing the asterisk, I'm going to run it here, and it just like seems to have not have worked, and we're really distressed. I'll just open a parenthesis here, go to the and painstakingly, and then I'm just going to add a cat, and then come on. How did that work? How did that not work? I am so alarmed right now. How did that not work? That should work. So I'm executing. So if I put back my all my stuff here, in this age, and then it should have a trace trap. Wait, what? So it reads all this stuff, and then it's a trace trap. Oh, is it the scanf? Oh, I see, okay. So I'm not even triggering the bug right now because I'm still reading things from standard input and it's being annoying. Okay, this is kind of a pity here. So scan if it's being, okay. Scan if reads it in, and then it doesn't actually proceed until it gets at least a new line. So we can provide that new line, and then we have our cat, So, provide it, but then I'm dead. We don't want to be dead. That is bad. Tell you what. We could. So here's another thing: is that you may not always be in a situation where you have an interactive prompt, right? Right. So this may be one of those situations where we have to kind of make do. So what we could do is that we could have. Let's make a different program here. We're going to call it temp yo.c, and yo is just going to print something out for us. It's just going to say printf, hey. Okay, it's showing us that something got executed, right? In fact, it's going to print it to standard error, and then we can try to have it execute bin bash or something, and whatever it wants to try to do. Let's try bin bash. Okay, so let's try this. Temp yo.c. Okay, can I type temp yo? Okay, it did execute shell. Okay, and now I'm going to just change my shellcode a little bit around here to execute temp yo instead of what it was doing previously, which was finish exactly the same number of characters, and let's see what happens now. Okay, so I'm going to skip the echo cat here. Okay, so the problem is just that the shell died. So what you could have hey do over here, this is just another thing, like the yo program over here, is to, let's say, you could do your set rest ID and all that stuff. Yeah, let's just do it. Go ahead and do it. Set rest ID 000. Now I'm going to do system copy bin bash temp root shell. Okay, and then I'm going to system chmod 4755 temp root shell. So it's a typical hacker thing. Okay, we do all this stuff. Last GCC thing here. I'm going to create extra privileges for this program called class. Shown class. Class. Okay. So now if that class is actually executed by root, and everybody's really excited because they could get root privileges. I'm going to run this, and it calls hey. What did it do? It created a root shell, which is owned by root, so that if I type root shell, I lose all my privileges. So let's make our yo program do something slightly different. We're going to have it not do bash, but zsh to root shell 2, because one didn't work. Okay, and we're going to do here history, and it's going to be 6885. And let's start it again. Hey, root shell 2. 2 ID. Oh, now we're root. Oh, there we go. Look, it's the blocks here. Okay, that wasn't quite what I intended, but at least it worked out for us. The problem if you have the format string one does not rely on standard input or anything like that, so you don't have to worry about this type of stuff. You'll just get a shell. But if you don't have a shell, literally, in fact, most remote exploitations, you don't have a shell. So it isn't. Yes. Make sense? Cool. Okay, we're over time. Cool. Thanks, guys.